my next example is going to be a simply supported beam with the pin over here at A and a roller over here at B. And I'm going to put a point load over here of 125 kilonewtons. And I've got 3 meters to the point load and 9 meters to roller B from the point load. This time I want to find the maximum deflection of the elastic curve. Okay, so looking at this, it looks to me like it's going to just bend down here and then come back up. So this would be my elastic curve. Now this is not symmetrically loaded and not symmetrically supported, so I'm going to assume that maximum deflection is occurring somewhere out here, delta max. Okay, but I don't know, let's prove it. Okay, first thing that I need is the equation for the elastic curve, and I'm going to do that with singularity functions. Okay, so I need my reactions at A, which is going to be 93.75 kilonewtons, and B, which is 31 1/4. And by the way, AX is equal to 0. I'm going to set the ordinate of my coordinates at A, so this would be my little v, and this would be my x. Looking up here at my table, all of my forces are points, so it's just going to be the second row here that comes into play. My moment equation is going to look like 93.75 bracket x minus 0, 1 minus 125. Again, that arrow is pointing down, so we need to change the sign. X minus 3, 1, plus 31.25, x minus 12, 1. First integration, theta EI, 93.75 divided by 2, x minus 0 squared, minus 125 divided by 2, x minus 3 squared, plus 31.25 divided by 2, x minus 12 squared, plus my constant of integration, 1. For my elastic curve, I'm going to have 93.75 divided by 6, x minus 0 cubed, minus 125 divided by 6, x minus 3 cubed, plus 31.25 divided by 6, x minus 12 cubed, plus c1x plus c2. All right. I need to solve for my constants of integration. So boundary conditions again. And this time we have a pen and a roller. So that means the vertical deviation at the pen and the roller is equal to 0. The pen is at x is equal to 0, and the roller is at x is equal to 12. So let's do those two equations. We're going to have 0 is equal to 93.75 divided by 6 times 0 minus 0 plus 0 plus c1 times 0 plus c2. c2 is equal to 0. Next up, we have, I want to make sure that's still on there, 0 is equal to 93.75 divided by 6 times 12 minus 0 cubed minus 125 divided by 6 times 12 minus 3 cubed plus 12 is equal to 12, so that's 0 plus C1 times 12 plus C2 that we solved for earlier as 0, and we find that C1 is equal to negative 984.375 with 6 significant digits. Okay, now we have our constants of integration solved for, then what? Now we're going to do the slope equations, because if I look back up here, where is the maximum deflection? Well, that's when the curve changes shape. That's the vertex, right? So that's where slope is equal to 0. So that's what I'm going to do. Delta max at theta is equal to 0. So try theta equals to 0 for 0 less than or equal to x less than or equal to 3 meters. Okay? Why that? Because that's my first change, right? I've got a pin to the load, so it could either happen at that change or from 3 to 12 meters, right? So those are my two options. So I'm going to pretend it happens from 0 to 3 meters. So theta is equal to 0 is equal to 93.75 divided by 6 divided by 2, we're using theta, goodness gracious, times x minus 0 squared. So I want this one because x can be greater than 0, so that means a is greater than 0, so we're good. Minus, okay, the next one here is 125 divided by 2 times x minus 3. Okay, well, if we're less than 3, greater than 0, less than 3, there we go, accurately written. And that means this is 0, as is the last one. And then we just have C1, which is minus 984.375, meaning my options for x are positive or negative 4.5826. Okay, neither of these are good. Negative is bad because it is less than 0, and 4.5826 is greater than 3. So neither of those answers is going to work. So we do not have a maximum deflection from 0 to 3 meters. So let us try. Theta is equal to 0 for 3 meters. See, I was going to put the equal to again. Less than x less than 12 meters. Okay, let's try it there. So that's going to be theta, which is equal to 0, is equal to 93.75 divided by 2. No, I don't simplify. I'm lazy. X, because it should be greater than 0, squared. All right, and then we've got minus 125 divided by 2 times x minus 3 squared, because it should be greater than 3, so it's greater than a, plus it's still less than 12, so this last term is 0, plus C1, which is minus 984.375, and I get x is equal to 5.2918 and 18.7082. Okay, this last term is no good because it is greater than 12. This term, however, is good because it falls between 3 and 12. Yay, we found an answer. Okay, for some of you thinking, what happens if I have 2 correct answers? Then you try both and pick the biggest magnitude for the maximum deflection. in this case, we only have one answer. So V EI is equal to 93.75 divided by 6 times 5.2918 minus 0 cubed minus 125 divided by 6 times 5.2918 minus 3 cubed, okay, plus 0 because it's still less than 12, minus 984.375 times 5.2918, and then plus C2, which is 0. Therefore, V max or delta max is equal to negative 3,144 kilonewton meters cubed all over EI. The negative sign indicates that the deflection is acting down, which it should because we're pushing down with the load.